Hey kids, Charlie Busso here. Guess homework number 3. State Avogadro's hypothesis perfectly. Ready? Here we go. Equal volumes of different gases at the same temperature and pressure have the same number of particles and same number of moles. Now, I almost wrote right here, I almost wrote atoms or molecules, but particles includes both. Gases can be atomic, like the noble gases, or gases can be molecular, like carbon dioxide, but it's the same number of particles and the same number of moles. Equal volumes of different gases at the same temperature and pressure have the same number of particles and the same number of moles. Write a chemical formula for any two real gases. All right, here we go. Carbon dioxide, oxygen, and then the noble gases. We have helium, neon, argon, xenon, krypton, and radon. Also, we have methane. We can have H2O gas if it's hot enough, right? Huckelbrief twins, H2, O2 we already have, N2, Cl2. The rest of them are not. Oh, I missed F. Yep. F2. The rest of them are all liquids. It's a lot of gases. There are no formulas for ideal gases. There are no such thing as ideal gases. Ideal gases are the idea, the theoretical, magical, perfect gas. All gases are real. Ideal gases are kind of like the ideal teacher. They don't exist. Teachers try to be good, but they do not ever become perfect. Under what conditions of temperature and pressure? A high temperature and low pressure equals most ideal. Now, how come? Because at high temperature, the particles are bouncing around so fast and so hard, they probably are not going to turn into a liquid. And at low pressure, they're moving around, but they're bumping into each other very, very unoften. That's not even English. They're not bumping into each other too much. The less likely it is to turn into a liquid, the more ideal they are. Now, in this particular one, we have CO2, helium, and this one here happens to be called propane. They're all at these silly same pressure, same temperature. It doesn't matter what the pressure and temperature are, they're the same. Which is most ideal? This would be the most ideal, and this would be the least. Smaller is most ideal. Particles that are smaller have less intermolecular attraction, and therefore they are less likely to turn into a liquid. All three of these gases are gases at this pressure and temperature. But if we had to decide which is the most ideal, you'd have to pick. If you looked at three hamburgers and decided which one is most ideal, you don't have to eat them. They are. One is more ideal than the other based upon how you liked it cooked. And what is it got mayo on it or ketchup on it or mustard or both? You know, whatever it is. Now, all three of these gases are gases, but one in fact can be determined to be more ideal. The smaller the particles, the more ideal it is. Now, this next one, number 5, let me give myself some room here. You have a volume of carbon dioxide gas at STP, it's changed, constant temperature. Constant temperature, that means we're going to use this formula, P1V1 equals P2V2. Constant temperature, that's a volume, and the pressure is here. And we're going to kPa. So we're going to start out with 101.3 kPa, and the volume is 32.5 liters. What's the new volume if it's changed to 75.0 kPa? So we got to get the V2 by itself. We're going to divide both sides by 75.0 kPa. 75.0 kPa. On this side, it completely cancels. On this side, the kPa's cancel, and we have a math problem. Let's see if we can do this math here together where you could see it. It's going to be 101.3. Oh, let me get this on. 101.3. And it's going to be times 32.5 equals, and then divided by 75.0 equals, and the answer is going to be 43.9 liters. Okie doke. Next up, number 6. The pressure on this volume is this pressure at that temperature. We chill it, the volume, what's the new pressure? In this case, we're going to have to use the whole formula. P1V1 over T1 equals P2V2 over T2. The pressure, 101.3 kPa on 125 liters at 275 Kelvin is changed. The temperature goes down to 155 Kelvin. The volume becomes 65.0 liters. What's the new pressure? What's the new pressure? What is the new pressure? P2. So to get this by itself and organize, we have to cross multiply. So we're going to cross multiply this way and this way. So I'm going to do P2 times 275 Kelvin times 65.0 liters. See, I did that? I did these 3 units here, and that's going to equal the opposite, 101.3 kPa times 125 liters times 155 Kelvin. This is the setup. Now, in order to get P2 by itself, we have to divide both sides by this. So I'm going to divide this side by 275 Kelvin and 65.0 liters. And then on this side, I'm going to divide 275 Kelvin and 65.0 liters. Now, I know this is tight, but watch what happens. This cancels and this cancels, so we get P2 by itself. On this side, we got this Kelvin cancels with this Kelvin, and this liters cancels with this liters, and the unit comes out in kPa. And that's the only thing we have to do. Now, I'm going to slide this over so we can do this. We're going to do the math for the top first. I'm going to multiply these numbers. 101.3 times 125 times 155. And I got to write this number down. 1962687.5. And that's my numerator. I'm going to hit clear. Now I'm going to multiply the bottom numbers. 275 times 65.0. And that's going to be here, 17875, and the unit's kPa. So to get this answer, I'm going to do this math problem. 1962687.5 divided by 17875 equals, you see this? Up with the glare. We need, looks like 3 significant figures. So it's going to be, I'm going to squeeze it over here. 110 kPa. And that's actually the answer. 3 significant figures. All right. See? 109.8 rounds to 3 significant figures. All right. Last 2 problems. I think I'm going to switch to pen. My pencil is getting a little bit too dull, and I don't want to get up. Number 7. A sealed container with constant volume has nitrogen gas. We have this crazy number, 1.00 times 10 to the 3rd pressure in kPa in 20 centigrade. The cylinder heats up to 50. What's the new pressure? Our constant volume. When pressure and temperature change, but volume is constant, we have P1 over T1 equals P2 over T2. Oh, look at this. That pen goes right into the recycle bin. Here we go. So we have this crazy pressure. So it's going to be, let's just leave it, 1.00 times 10 to the third kPa over 20 degrees. I'm pointing, you can't see it. 20 degrees. That's another way to say 293 Kelvin. Can't use centigrade. If it heats up to 50 degrees, 273 and 50 equals K. K equals C plus 273. K is going to equal, I can do it in my head, but I want to show you guys that you should do this. 50 and 273, 323, and P2. So we have some crazy pressure, annoying the way that number is written, but if we change it to 1,000, we'd have to remember three significant figures. So we'll crisscross multiply. So it's going to be P2 times 293 Kelvin, right? I did this. And now going across this way, it's going to equal 323 Kelvin times 1.00 times 10 cubed. Oh, kPa. We're going to divide both sides by 293 Kelvin. And on this side, it all cancels out. So I'm squished for space again. P2 is going to equal this math problem. So I'm going to do 323 times 1,000 equals, divided by 293 equals, and I have to have three significant figures. Oh, this is annoying, 1102.389 kPa. But with three significant figures, it's going to be 1.10 times 10 cubed kPa. 1.10 times 10 cubed kPa. Last problem. You have gas with a volume and a pressure. It expands till the pressure drops. What's the new volume? Temperature remains constant. With constant temperature, we have P1 V1 equals P2 V2. A gas with this volume at this pressure, so pressure is going to be 90.0 kPa and volume is 4.0 liters. Pressure drops to just 20 kPa with three significant figures. What is V2? What is the new volume? We're going to divide both sides by 20.0 kPa. This side cancels out. Here the kPa's cancel out. And V2 is going to equal this math. So let's do it. We have 90.0 times 4.0 equals, divided by 20.0 equals 18. Now we have to look, we got two significant figures here, so it's going to be 18 liters, and that's the answer. Now, the most important thing I guess you have to worry about here with the gas law problems is there's a lot of freaking words. Numbers, units, everything. You got to put things in the right place. We got fooled before. Well, what was the start? What was the end? What was the starting condition or the end condition? You just got to put stuff in the right place. And then the math will work out. Watch your significant figures.